This video demonstrates how we can use a live signal simulator against a production design to develop a control solution on the bench before we need to bring it out to actual hardware. So what you see is for the EdgeGuide controller, the paper roll position controller is the production PLC programmed in C. On the scope, yellow trace is the paper edge sensor, blue is the LVDT sensor. This little box here, this is the plant. Well, this hosted by the PC and the plant model is implemented in C, but from a signals perspective, this is the plant. The plant takes the command output, the orange wire, that's the servo valve amplifier voltage command, runs that through the plant model, difference equations, maps the lateral motion that's modeled to LVDT output, also models the transport lag to the paper edge and outputs the edge sensor signal modeled. And likewise, from the simulator, independently, the speed pulse to simulate the drum speed is fed into the controller. So what this controller is then doing is implementing our proportional and integral control schemes, outputting a command through the plant model, again, conditions the sensor output back to our production controller. So it can get a little confusing. What's an input? What's an output? The command's always an output from our plant, from our controller into our plant, and our plant, of course, is responsible for sensor signals, which are outputs here and inputs to the production unit. And then again, the speed pulse is an input. So that's the setup. And if I jog the plant, you will see that on the screen, I put in a step response. I'm only going 738 feet per minute, but now you can see this is accounting for transport lag in the system, and that's why we get a fairly relaxed response. If I do this again at a higher speed, I'm going to do this again. I'm going to speed up. I'm going to go from 730 feet per minute. I'll just go up to a couple thousand feet per minute. Now I went too slow, but now I'm going fast. I got a lot more gain at high speed because transport lag is reduced. And now an equivalent step disturbance to the paper edge is responded to much more rapidly, which you can see in the yellow trace on the screen. And I can give short disturbances. These are just smaller steps, and you can see the edge sensor. We'll move this closer to the oscilloscope. You can see the edge sensor respond to those. I can't remember how many millimeters disturbance that's modeling. So we have variable gain according to speed, and we're able to develop all of the code for the controller, which is here, also in C. And we work out our design, bench test it, iterate in this environment before needing to hit the shop floor, install, and run live production material through a machine. So this is imperative in almost all controlled design environments. You might start with a purely software simulated environment where you're not simulating with live signals, but when possible, simulating the whole thing with live signals is incredibly useful because you can solve and resolve your numerical problems, sampling issues you may have, filtering, and you're also able to simulate noise and other conditions in your simulator environment, which in this case is the other side of the code. So that code running the simulator is here, and if I hide the video for a second, you can see it's got a little bit of keyboard input, moving the edge. I guess I modeled the small steps as 5 millimeters, the larger steps as 5 centimeters. So when you saw the faster and slower responses there, not relative to speed, but just a quick response to a small disturbance, that's because that was 5 millimeters. And then this is speeding up and speeding down. We read our command in. We run that command in through a model. So we run it through a model, and our model is implemented as a difference equation. If we go to that code, I think it's in the analog in here, command in. So our command comes in, we condition it as we expect it to be conditioned by the servo amplifier, and we run it through our plant model. And the parameters, you'll recognize this is just a difference equation. And then the storage that you see down here is retaining a time history so that we can account for the transport lag in the other part of the design, and I'll skip that part. So we're using our S-domain model, if you will, our system identified model for the actual plant in difference equation form here to then utilize this as a design tool. And we're able to get our entire system, which is this code here, designed on the bench. And you have to account for sampling rates. This the production code runs at 100 hertz, sample rate of 100, and the simulator is running at, I think, 400. So you'll have to account for those. You say one could beat against the other. You'd want the simulator to be considerably faster than the controller in this case, but those are the sorts of considerations that you make in implementing a scheme like this. So critically important design methodology. How to design production hardware against the simulator, and where possible in a live signal environment, live signal, and even live sensor environment where that's possible.